You ever look at a circuit board and just see, a total mess of lines and little components? It looks impossibly complex, right? But what if I told you all that complexity is built on just a few surprisingly simple ideas? Well, today we're going to pull back the curtain and demystify the entire world of electric circuits.
So, let's kick things off with a little mystery. Your standard car battery, it's just 12 volts. But to get a spark to actually ignite the fuel in your engine, you need thousands of volts. So how on earth does that happen? Well, it's not magic, it's actually a really elegant application of the principles we're about to break down.
And this isn't just about what's under the hood of your car. The exact same principles that solve that battery puzzle are beating at the heart of pretty much every piece of modern tech you can think of. Your phone, the factories that build our world, it all comes down to telling electricity where to go and what to do.
Okay, so to understand the whole system, you've got to start with the pieces, right? We're going to deconstruct all this amazing technology into its most basic, most fundamental components.
When you crack open an engineering textbook, the diagrams can look absolutely insane. But get this, every single one of those systems, no matter how wild it looks, is built from just a handful of simple little parts. Kind of like this humble resistor you see here. It's like you have to learn the alphabet before you can write a novel. These are our letters.
All right, first up, the resistor. Think of this little guy as a traffic cop for electricity. Its whole job is to push back, to create resistance and manage just how much current gets to pass through. It is one of the most fundamental tools for controlling the flow in a circuit.
Next, we've got the capacitor. Now, this component is all about storage. It acts like a tiny little battery that can charge up and then discharge in a flash. It holds on to energy in an electric field, just waiting for the circuit to need a quick jolt of power.
And our third key player is the inductor. So, while a capacitor stores energy in an electric field, the inductor stores it in a magnetic field. And it has this one really cool trick. It absolutely hates sudden changes in current. It works to smooth everything out, fighting against any sudden spikes or drops. Now, pay close attention to this one, because its unique little personality quirk, that's the secret to solving our whole car ignition puzzle.
So, we've got the parts: resistors, capacitors, inductors. The building blocks. But just having the pieces isn't enough, right? Now we need to understand the rules of the game, the elegant, fundamental laws that dictate how electricity actually behaves. And these rules weren't just found lying around. They were pieced together bit by bit over decades by some seriously brilliant people. Volta gave us the battery, our first steady source of electricity. Ampere figured out what current even was. And George Ohm, well, he gave us the law that ties it all together. It's an amazing story of human curiosity, literally building the modern world.
And that brings us to the big one, Ohm's law. It's this beautiful, simple, but incredibly powerful idea that connects three things. You've got voltage, which is like the electrical push. You have current, which is the actual flow. And you have resistance, which is the pushback against that flow. This one simple law is the absolute cornerstone of all circuit analysis.
And to make this super intuitive, let's use a classic analogy. Just picture electricity in a wire like water flowing through a pipe. The voltage, that's like the water pressure, pushing it all forward. The current, that's the flow rate, how much water is actually moving past a point. And the resistance, that's like a narrow section of the pipe, making it harder for the water to get through. See? It's a really helpful way to visualize what's actually going on.
And hey, don't just take my word for it. The source material says it loud and clear. Ohm's law and a few others form the absolute bedrock of electric circuit analysis. Everything else, literally everything, is built on top of this foundation.
Okay, we've got the parts, we've got the rules. So how do we actually use them to solve problems, like that car ignition mystery? This is where we learn to think like an engineer.
And it's not just about winging it and crunching some numbers. There's a method, a process. You start by defining the problem really clearly. You lay out everything you know. You brainstorm a few ways to tackle it, you try one out, and then, this is the crucial part, you evaluate your answer. Does it work? Is it accurate? Does it even make sense in the real world? It's a disciplined way to get from theory to a real solution.
And that same fundamental process is exactly what engineers are doing today, just supercharged. They use these incredibly powerful computer programs to apply those exact same steps to circuits with millions, sometimes billions of components. The tools are way more advanced, but the core thinking, it's exactly the same.
So let's zoom back out for a second. Why does getting a handle on these building blocks and rules matter so much? Because, well, understanding them is the key to designing the future.
I mean, really understanding circuits opens up a frankly ridiculous number of career paths. You want to design the power grids for our cities, build the next generation of computers, create the control systems for self-driving cars and robots, pioneer new ways for us all to communicate. It all starts right here, with these fundamentals.
And the scale of it all, it's just mind-bending. The same laws that tell electrons where to go inside a tiny microchip also govern the complex systems that power our space probes, letting us explore the cosmos and see these breathtaking images of our universe. These principles are truly universal.
So, let's close the loop. Let's solve our mystery. How does a little 12-volt battery create thousands of volts? The secret sauce is the inductor. Remember how it hates sudden changes? Okay, so the car's ignition system lets current from the battery flow, building up a ton of energy in the inductor's magnetic field. Then, right at the perfect moment, it suddenly cuts the power. The inductor completely freaks out. It tries desperately to keep that current flowing, so it dumps all of its stored magnetic energy at once in a massive, massive burst. And that creates a voltage spike of thousands of volts, more than enough for a spark. It's such a clever, elegant solution. So you see, these aren't just abstract rules in a textbook. They are the fundamental laws of our modern world. The only question left is, what will you build with them?